Mass spectrum interpretation, pentane and isopentane. Here is the mass spectrum of pentane, of the molecule pentane. The peaks that you see here is going to correspond to the m by z value of the different fragments that are obtained in the mass spectrometer. And the peak with the highest m by z value, here in this case, m by z equals 72, is going to correspond to the molecular ion, which is the one that is obtained when you dislodge an electron from the neutral molecule. And since we are not sure which bond is going to lose the electron from the molecule, we are generally going to represent the molecular ion within brackets with also writing down the positive and the unpaired electron on the side of the molecular ion. The other peaks that you see in the mass spectrum with smaller m by z values are positively charged fragments which are broken down from the molecular ion. And the tallest peak in the mass spectrum is generally called as the base peak, which has the greatest relative abundance because it is formed by the most stable fragment. And the relative abundance of the rest of the peaks are shown as a percentage of this base peak. We know that the mass spectrum is going to give us some structural information about the compound, but it is going to be based on two important things. The first thing is that the weak bonds are the ones that is going to break in preference to the strong bonds. And the second thing is the most stable fragments are formed preferentially over the less stable fragments. These are the two important things that we have to keep in mind in analyzing the mass spectrum. Now let's see what are the fragments that will be obtained when the molecular ion of pentane undergoes fragmentation. Now by looking at this molecule, we can definitely see that there are no electronegative atoms, right? So because of which we can definitely imagine that all of these bonds, carbon-carbon single bonds, they're going to have about the same strength. And all of these bonds can break equally. When you break across the C1-C2 bond, it's basically the same as breaking across the C4-C5 bond. And similarly, breaking across the C2-C3 bond is the same as breaking across C3-C4 bond. So now we have two possibilities. We can break across the C1-C2 bond or break across the C2-C3 bond. Let's do the two different scenarios and find out what are the fragments we'll be getting for these two different scenarios. Okay, now let's break across C1 and C2 bond. When you break across the C1-C2 bond, you get two different fragments. Let's say that you have only one electron. Remember, we are talking about the molecular ion, which means one of the bonds is going to have one electron. So let's imagine that we only have one electron here. This one electron can go on to either this carbon or it can go on to this carbon. Let's say if it had gone to the methyl carbon, then this carbon will have a positive charge on it. Let's write down the two fragments that we'll be getting. It would be a methyl radical and a primary carbocation. And you can also have the other possibility where the electron has gone onto this carbon, in which case the methyl carbon is the one which is going to have the positive charge. So this would be the other possibility. Okay, so these are the fragments that are obtained when you break across the C1-C2 bond, right? Now let's see what are the fragments that are obtained when you break across the C2-C3 bond. So you're breaking across the C2-C3 bond, and here again you will have two options. So if the electron is going to go onto this carbon, then this is the carbon which has the positive charge. So let's write it down. It's going to be a ethyl cation and a primary radical. And similarly, if the electron is going to go on to this carbon, then this is the one which is going to have the positive charge. So you will have an ethyl radical and a primary carbocation. So these are the two possibilities. Now let's take a look into this. Between these two fragmentation patterns, okay, so let's say that this is the C2-C3. Between the C1 and C2 bond breaking and the C2 and C3 bond breaking, which one is going to lead to the most stable fragments? Now here we have a methyl radical and a primary carbocation, and a methyl cation and a primary radical. Now we know that the stability of the carbocations and the radicals is going to follow this order. where the tertiary radicals or the carbocations is going to be more stable compared to the secondary, and then comes the primary, and then finally the methyl carbocations or radicals. Basically, the stability of the carbocations and the radicals are going to be following the same order. Here, you are forming a primary carbocation and a methyl radical, okay, which is comparatively less stable than the primary carbocation. But here, you are forming two primary carbocations. See, so which is definitely going to be more stable than the ones that are formed here. And therefore, we can definitely assume that the C2C3 bond is the one that's more likely to break. One of those fragments that are going to be formed is the one that corresponds to the base peak. Now let's identify the different the M by Z values of the different fragments that are obtained. So the M by Z value for this is going to be 43, right? And the M by Z value for this is going to be 29, and for this one it is going to be 57, and for this one it's going to be 15. Now, how the mass spectrum is interpreted is you're going to subtract the loss of the species from the molecular ion to get the M by Z value of the positively charged species. So let's say that this is your molecular ion, right? Molecular ion for pentane. So the peak at 43 is going to be corresponding to the loss of the ethyl radical. The ethyl radical has a mass of 29. So you're going to subtract the 29 from 72. So when you subtract 29 from 72, what you get is 43, which is going to be corresponding to the base peak, since this is the peak that you see as the tallest peak in the spectrum. And similarly, for the ethyl carbocation, there needs to be a loss of the propyl radical. So the propyl radical is going to have a mass of 43, and you're going to subtract it from there, and that is going to correspond for the ethyl carbocation. And similarly, when you come to the C1C2 breaking of the bond, you have to subtract 15 for the loss of the methyl radical to form the peak at M by Z value equals 57. And similarly, for the methyl carbocation, you needed to subtract a loss of 57 to account for the M by Z value of 15. Also remember that you're going to have the M by Z values only for the cations because they are the ones that will be identified in the mass spectrometer. You can have peaks 2 units lesser than the carbocations, and that is going to correspond to the loss of hydrogen. Let us now compare the mass spectrum of pentane and isopentane, which are constitutional isomers. Now, because they are constitutional isomers, they are going to both have exactly the same molecular formula, and the molecular ion peak are going to exist exactly with the same M by Z value. Right? Now, the only difference between these two compounds is the intensity of the peak at M by Z value equals 57, which corresponds to the loss of methyl radical. So this is going to be the loss of methyl radical. Now, what is the reason why isopentane should have a very strong, very intense peak at M by Z equals 57? That is because it forms a more stable secondary carbocation than what is formed in the case of pentane. Now, if you take a look into the structure, so if we're going to draw the molecular ion, this is how it's going to be, right? And if you're going to break about the C1C2 bond, it's going to result in the formation of the methyl radical and a carbocation. And the carbocation that is formed in this case is going to be a secondary carbocation, right? Whereas in the case of pentane, it is going to be a primary carbocation. And the primary carbocations are less stable compared to the secondary carbocation. And since the mass spectrum is going to show a sharp peak for the most stable fragment that is formed, here you see a much intense peak for isopentane, which corresponds for the secondary carbocation.